Hello class. In this lesson 1.6, Symmetry, Even and Odd Functions, you will learn to use graphs to determine the types of symmetry that exist. Now, a graph could be symmetrical in one of two ways. We can have a graph be symmetrical over an axis, which obviously means we have two axes in our coordinate plane. So we could have a graph be symmetrical along the x-axis, which means that the top portion of our graph will match up to the bottom portion of our graph, or we can have the graph be symmetrical along the y-axis, which then just means that the left half matches perfectly over the right hand if I was to fold it in that direction. The other type of symmetry that exists is the symmetry over the origin. That type of symmetry exists when graphs are unchanged when we rotate the graph 180 degrees. So if I simply again flip it, again 180, 290-degree angles, whether it's to the left or to the right, I will see that the graph again remains unchanged. So let's first start and discuss again symmetry over the axis. We'll begin with the symmetry to the y-axis. If something is symmetrical to the y-axis, then that means that for every x and y on the graph, for every coordinate plane on the graph, then the point negative x, y is also going to be on the graph. Negative x, y is also going to be on the graph. We can figure this out algebraically by simply replacing all of the x's with a negative x, replacing the x coordinates with a negative x, and simplifying and resulting in equivalent functions. Any relation or function, better said, that is symmetrical to the y-axis, because it will be a function, is referred to as an even function. So if something is symmetrical to the y-axis, it is also classified as an even function. So let's look at some examples of this. If you look at this example right here, we can clearly see by the graph that this graph is symmetrical along the y-axis. The left side of the graph matches perfectly again with the right side of the graph. To see this algebraically, one simply needs to do is replace the x value with a negative x and simplify and see if you end up with the same thing that you start off with. See if we end up again with this same equation there, which we are, because the absolute value of anything inside here again is the same as if it was positive. Then having a negative x inside there is the same thing as having a positive x. I'm still going to get the exact same value. So I'm going to get that y is equal to negative absolute value of x minus 2. So as you can see again, these results are equivalent, and hence how we test and algebraically if our graph is symmetrical along the y-axis. And because it is, this is referred to as an even function. So as a y-type symmetry, thus referring this function as an even function. Let's look at another example. This example here, again, can be by using the graph, can clearly see that this is symmetrical along the y-axis. The left side matches perfectly with the right side. So for this equation, replacing the x values with a negative x will help us again prove this algebraically, that this has a y-type symmetry. So notice again that an even factor of negatives, again this negative raised to the 4th power, is going to give me an even factor of negatives, making that positive x to the 4th power minus 4. And the same thing is true here. Having an even number x to the second, or negative x to the second, an even number of negative factors is going to give me a positive x to the 2nd power. And just like the previous example, we end up with an equivalent equation to what we start off with. Thus, again, confirming that this graph has a y-type symmetry, meaning that this is an even function. Now let's look at example number 3. Oh, I'm sorry. Before we look at example number 3, let's discuss the second type of axis symmetry, which is the symmetrical to the x-axis. Now, if something is symmetrical to the x-axis, that means that for every point x, y on the graph, x negative y is also on the graph. Replacing the y value with negative y, you're going to result in equivalent equations. Now, for the most part, actually for every situation like this, when something is symmetrical to the x-axis, this is not a function. This is just a simple relation. And you'll see again on the first example, example number 3. You can clearly see that this graph here, this equation, is a relation and not a function. The vertical line test fails, so this is not a function. So this cannot be classified as an even or an odd function. Now, if we look at this example here, we can see that the graph is symmetrical along the x-axis. Notice that the top parts matches perfectly with the bottom parts. Now, if you pay a little bit more closer attention, you could also even make the argument that it's also symmetrical along the y-axis, okay? Meaning that the left part matches perfectly with the right part, which is in fact true. This does have that type of symmetry as well. But we're going to simply just focus right now on the x-axis symmetry. So to prove this algebraically, to verify this again using the equation, we are going to replace the y value with a negative y and see if we end up with the exact same thing that I originally started off. And I am. Negative y to the second power has an even factor of negatives, so that it's going to give me positive y to the second power minus x to the second power is equal to 1. So you see it matches perfectly again to what I originally had. So this is symmetrical along the y-axis. I'm sorry, the x-axis, So this is an x-type symmetry. So this has an x-type symmetry. Now, it also has a y-type symmetry, as you can see by looking at the graph. Let me erase this. It does have a y-type symmetry, as you can clearly see here. The left part matches perfectly with the right part. So we also fold it along this yellow line. The left and the right will overlap, would match up perfectly. Algebraically, we can verify that by replacing the x with a negative. Simplifying that's going to still give us y squared minus x squared is equal to 1. For the same reason as before, we have an even factor of negatives. So negative times a negative is still going to give us positive. Bringing down the negative sign again, we end up that this matches exactly what we started off with. So as a result, again, this also has a y-type symmetry. However, this is not an even function because it's not a function. So this is not even though. This does not get classified as even. It just has those two types of symmetry. It has an x-axis symmetry and a y-type symmetry. Let's look at another example. See how this example has only an x-type symmetry. The top part of the graph matches perfectly with the bottom part of the graph. We can verify this algebraically by replacing the y value with a negative y. And just like before, because we have an even factor of negatives, negative y to the second power is going to become positive y. Notice again that our equations match. This equation is equivalent to having a negative y. They are equivalent. So this has an x-type symmetry, x-axis symmetry. I should use the word axis instead of type, but the same idea, x-axis symmetry. Now the last type of symmetry again is the symmetry through the origin. For something to be symmetrical through the origin, that means that for every x and y value on the graph, negative x and negative y is also on the graph. So replacing x with a negative x and replacing y with a negative y is going to result in equivalent equations. For example, this one right here. Before I look at the graph, I'm going to again look at the equation. And look what happens when I replace both the x with a negative x and the y with a negative y. Well, here, the negatives and negative again, it's an even number of negatives. They're going to multiply to become a positive. So I end up again with positive x and positive y is equal to 6. So again, I have the equivalent equation. So this again is symmetrical through the origin. And because it's symmetrical through the origin, which I didn't mention on the last slide, let me go back over here. Any relation that is symmetrical through the origin and only through the origin, okay, which I should emphasize on that, is referred to as an odd function. So this example has only this origin symmetry and thus is referred to as an odd function. Graphically, this simply means that if I rotate this 180 degrees, flip this upside down, the graph will look exactly the same. So this is kind of hard to do again, to flip this a still picture upside down, but you should be able to see that this again is going to be the exact same graph this way and 180 degree rotated. Let's look at the last example. In this example right here, it has no type of symmetry. No matter algebraically, there's nothing again to do. If I put a negative y here, I do not get the same thing. If I put a negative x there, I do not get the same thing. So everything is going to become different. Graphically, you can clearly see that these graphs again are not symmetrical. Not through the y-axis, not through the x-axis. And if I was to rotate this 180 degrees, the graph would not look the same. So this has no type of symmetry at all. All right. Well, that concludes the lesson on symmetry, even and odd functions. Now recall that for a function that's symmetrical through the origin, those are referred to as odd functions. And for functions that are symmetrical through the y-axis and only the y-axis, they're referred to as even functions, like number 1 and number 2. Those are referred to as even functions. But if something is symmetrical through the x-axis and the y-axis, or the x-axis and the origin, then it's not an even or an odd function, okay? Not a function at all. Like in this example right here, even though this is symmetrical to the y-axis, it is not referred to as an even function because it also has that x-type symmetry, that x-axis symmetry. And let me just change those words. All right. Okay, well, that concludes this lesson, like I said, on symmetry, even and odd functions. I hope this was very helpful. If you have any questions, again, please send me a message or a reminder. Thank you again for watching and have a great day.